Hello YouTube! Today I want to talk about web security, how to make your application safe, how to prevent data leaks, and how to protect yourself or your company from huge financial losses if a breach happens. Security is also a topic you will face at almost every job interview, regardless of the company or your level. Trust me on this, because I have conducted multiple interviews myself and been interviewed many times as well. If you're here for the first time, my name is Dima. I'm a senior software developer from Berlin with 8 years of commercial experience across different companies, mainly in fintech, where security usually is high priority. So I have hands-on experience with the topic. Let's dive in. Let's start with a fundamental question. Why should we care about security? And I'm not talking about some abstract, it's important answer. I mean the actual concrete reasons that affects you and your company. There are two main reasons here: user trust and reputation, and financial and legal consequences. On the user trust side, think about what happens when there is a security breach. Users trust you with their payment information and personal data. One security breach destroys that trust for a long time. They might switch to competitors, and your company's reputation takes damage that lasts for years. Look at what happened with Equifax in 2017. They had a breach that exposed data of 147 million people, and they are still dealing with the fallout. On the financial side, GDPR fines can go up to 20 million euros or 4% of revenue, whichever is higher. Then you have lawsuits from affected users, and the recovery and incident response costs run into millions. For example, British Airways paid a 20 million pounds GDPR fine for a 2018 breach. So when we talk about security, we're talking about protecting real money and real users. Now you might be thinking, isn't security the security team's job? Well, yes and no. Usually all employees in the company are responsible for security, but let's look at four main groups. The development team writes secure code in production. The security team provides expertise and oversight. Operations and infrastructure handle infrastructure security, and leadership and management set policies and budgets for security initiatives. Security isn't just one team's problem. It is a shared responsibility across the entire organization. As a front-end developer, you're writing code that handles user data, renders content, and makes requests. So a lot of security depends on the decision you make every day. Let me tell you who might find this video useful. First, developers building applications. You're responsible for protecting user data. You need to understand security because you implement code in production. The choices you make directly affects whether your application is vulnerable or not. Second, developers preparing for interviews. In many companies, you will be asked about security during technical interviews. Interviewers want to see that you understand common attacks like XSS or XSRF, and more importantly, that you can explain which defenses make sense in different situations. It is not enough to know what XSS is. You need to understand the trade-offs between different defense approaches. Before we dive in, let me give you an overview of what we're going to cover. We'll start with threat modeling, basically how to think about security systematically. Then we will break security into three areas: security on the front-end side, security in transition between client and server, and security on the backend side. Let's talk about threat modeling first. This is a systematic way of thinking that helps developers identify what could go wrong before it actually happens. Threat modeling is basically asking yourself, if I were an attacker, how would I break this system? You go through your application methodically and think about potential vulnerabilities at each layer. Let me show you how to create a threat model for a typical web application. You usually start by drawing your system architecture, not in details, but the main components. For a web application, that typically means sections: the client side running in the browser, the data transition layer where information travels over the network, and the backend with your servers and database. Then, for each section, you ask specific questions. What data could be stolen at this step? Think about what sensitive information flows through each part. On the client side, maybe session tokens. In transition, maybe its credit card number being set to your payment API. On the backend side, the entire user database. How could an attacker access the system? What are the entry points? Forms where users submit data, URL parameters that get reflected back, API endpoints that accept requests. What are the weakest points in your system? You need to understand where yours are. Maybe you have an old admin panel that doesn't use modern authentication. Maybe you're using inner HTML, which is a dangerous method, to display user comments. Maybe your database queries concatenate strings instead of using parameterized queries. What would cause the most damage? Not all vulnerabilities are equal. Some might leak all user data, names, emails, passwords, payment information. Others might just let an attacker deface your homepage or spam your users with annoying pop-ups. That's bad, but it's not end of the world. You need to prioritize based on impact. And the final question, what defenses do we need? Once you understand the threats, you can decide which protections are worth implementing. Maybe you need CSP to prevent XSS. Maybe you need rate limiting to prevent brute force attacks. Maybe you need encryption at rest for sensitive database fields. The point of threat modeling is to think about security systematically instead of just hoping you didn't forget something important. It forces you to consider the attacker's perspective before they actually attack you. So when we think about threat modeling, we usually split application into sections. We start by asking, what should we defend on the client side? Then we look at the transition layer. What could happen during data transfer? And then the backend. What vulnerabilities exist on the server? Based on the natural threat model for a typical web application, we can identify three main areas where security matters. First, frontend side. This is about protecting what happens in the browser, preventing malicious scripts from executing, handling user input safely, controlling what resources can load. Second, security in transition. This is about protecting data as it moves between the client and server. We're talking about HTTPS, man-in-the-middle attacks, ensuring data can be intercepted or modified during transmission. And third, security on the backend side. This is about protecting your servers, databases, and APIs from attacks like SQL injection, authentication bypass, and unauthorized access. That's why we use these three categories. It's not just three random areas. It's a natural way of thinking about threat modeling for web applications. Each layer has different attack vectors and requires different defensive strategies. Let's dive into Frontend Security. This is where you have the most direct control as a front-end developer. The main we're going to focus on here is XSS, or cross-site scripting. It's one of the most common vulnerabilities in web applications. The core problem is this. Your application renders data as executable code. That sounds abstract, so let me make it more concrete. Look at the picture. A user makes a request to fetch comments. The server sends back data that might include a malicious comment. Maybe another user submitted a comment earlier that contains JavaScript code. Or maybe your database was compromised through SQL injection attack and now contains malicious scripts. Either way, that data comes from somewhere you can't fully trust. And here's the vulnerability. We put that comment into the page using inner HTML, which means any JavaScript in that comment will execute. There are actually two vulnerabilities shown here. The first one, we don't validate the user's input on the front-end side. The user can type anything, including script. And number two, we put potentially dangerous content onto the page using inner HTML method, which executes any script it contains. Anytime you take data from any source and put it into the DOM, you need to make sure it can be executed as code. Now, why is this so dangerous? When that malicious JavaScript executes, it runs with the same permissions as your legitimate code. It can steal the user's session cookie and send it to an attacker server. It can make requests to your API on behalf of the logged-in user. Remember, the user's browser automatically includes authentication cookies with every request. So the malicious script can transfer money, change passwords, delete data, whatever your application allows. It can redirect the user to a phishing site that looks exactly like your app logins page, or it can simply inject advertising or defacement content. This is why XSS is such a serious vulnerability. It gives attackers complete control over what happens in the user's browser on your domain. Now, there are actually three main types of cross-site scripting attacks, and they work differently. The first one, stored XSS, also called persistent. is when the malicious script is saved in your database. Every user who views the data gets infected. Reflected XSS is when the malicious script comes from the URL or request parameters and gets immediately reflected back in the response. It's not stored anywhere. And DOM-based XSS is when the vulnerability exists in the client's JavaScript. The server never even sees the malicious payload. It's all handled in the browser. Let's start with stored XSS. Step 1. An attacker submits a malicious input. Let's say your application has a comment form where users can post comments on articles. The attacker goes to this form and instead of typing a normal comment like great article or something like that, they type something like script alert script. Now, this is just a simple example. In reality, it could be any JavaScript code. This is malicious because it's JavaScript code embedded as a comment. When the browser executes this script, it can steal cookies, make unauthorized requests, redirect users, and basically anything JavaScript can do. The vulnerability here is that we are not validating input on the front-end side. The form accepts whatever the user types, including script tags and other HTML. And step 2, the server saves the malicious input as if it were a normal comment. The server receives the post request with this script tag in the comment field and just stores it directly in the database without checking what it contains. The vulnerability here is that we are not validating input on the backend side either. The server trusts whatever it receives from the client. And step 3. Another user visits the article page and the application requests comments from the database. So this is the normal operation, nothing wrong here yet. And step 4. On the front-end side, we put this server's response directly into the page. Inner HTML is a JavaScript method that lets you insert HTML into an element. The problem is that inner HTML is designed to work with HTML markup and executes any HTML or JavaScript it contains. So when we insert HTML via inner HTML, this data might contain any scripts and it will be executed. We assume we are only inserting safe HTML, but this is exactly the breach that a hacker can use to insert a malicious script. The vulnerability here is that we are not validating or escaping the server's response before putting it on the page, and we're using inner HTML, which is potentially dangerous. When that malicious script executes, it runs in the context of the logged-in user session. The user's browser automatically includes their authentication cookies with any requests the script makes. So the attacker's code can send, for example, a transfer money request to your backend, and the server will think it's a legitimate request from the logged-in user because the authentication cookie is there. Let me emphasize why stored XSS is especially dangerous compared to other types of attacks. And the first reason is persistent. The malicious code stays in your database until you clean it out. It's not a one-time thing. Second, it affects multiple users, not just the attacker. Every single person who views that comment gets infected. So one successful attack can compromise hundreds or thousands of users. And third, it's hard to detect. The malicious code might sit in your database for a month before anyone notices. During the time, it's quietly doing damage. This is why stored XSS is often considered one of the most serious web vulnerabilities. Quick note before we continue. This video covers a lot of web security fundamentals. If you want to dive even deeper, I have created the Advanced Frontend course. It's 8 modules covering everything you need to build complex web applications and prepare for senior-level interviews. We cover state management, real-time communication, system design, CI/CD, and more. Since the course just launched, there is a 50% discount with code Early Access and a 10-day money-back guarantee. No questions asked. Link in the description. Now, let's back to web security. Before we talk about how to defend your application against XSS attack, I need to explain 3 concepts that people often confuse: validation, sanitization, and escaping. These are related, but they're not the same thing, and understanding the difference is critical for building secure applications. So let me break down this table and explain when you use each technique. Validation asks, is this input valid? You're checking if the input meets your business or structural rules, not whether it's safe, just whether it's correct. For example, is this a valid email format? That's a business rule. You need a properly formatted email address. Not because wrong formats harm security, but because your application needs valid emails to function. Another example is the age between 0 and 120. If validation fails, you reject the input with an error. The output is either the original input or an error message. You use validation when you have strict rules that must be followed. The next one is sanitization. Sanitization asks, how do I make this safe? You are transforming or cleaning the data to remove dangerous content while keeping the useful parts. This is used when users need to include formatting in their text, like making words bold or adding links. The output is modified input. For example, you might remove script tags but allow bold tags. The key difference from validation, you are not rejecting the input, you are fixing it. You use sanitization specifically when allowing user markup like HTML or Markdown on your site, in places like rich text editors or formatted comments. And the third one is escaping. Escaping asks, how do I safely display this? Here's the key insight. You don't modify the stored data at all. You keep the original data exactly as the user typed it. Then, at the moment you need to display it or send it somewhere, you convert special characters so they can't be misinterpreted. For example, when displaying text in HTML, you can convert the less than symbol into the word $LT. So the browser shows it as a text instead of treating it as the start of an HTML tag. Why do we need this? Because we want to show users exactly what they typed, but we need to prevent the browser from executing it as code. The output is context-specific encoded output, different encoding for HTML versus SQL versus JavaScript. You are escaping when displaying, storing, or sending data into another context. So the fundamental difference is validation is for correctness, sanitization is for cleaning markup, and escaping is for safe display of any data without changing what's stored. Let's start with validation. This is about ensuring data is correct according to your business rules. Look at this code example. We have a function that validates email format using a regular expression. If the email doesn't match the pattern, we throw an error saying something like invalid email format. Otherwise, we return the email unchanged. Notice this is a business rule. We're not checking if the email is malicious, we're checking if it's a properly formatted email address. A wrong email address doesn't harm your application security, but your application needs valid emails to send notifications or identify users. Another example is how we validate age. If the age is less than 0 or greater than 120, we throw an error saying unrealistic age. Again, this is the business rule. Your application logic might need realistic age values, but an unrealistic age doesn't create security vulnerability. Here's what's important to understand. We are checking if the input meets our business or structural rules, not if it's safe. A perfectly valid email could still contain SQL injection code if you're not careful where you use it. Validation doesn't protect against attacks. It just ensures the data makes sense for your application. If validation fails, you reject it with an error. You don't try to fix it. You don't modify it. You just say no. Now, let's talk about sanitization. This is where we modify data to remove dangerous or unwanted content. You use this technique when you're allowing users to include markup in their input. In places like rich text editors, formatted comments, or anywhere users can write Markdown or HTML. The code shows us two examples. For HTML sanitization, we use a library called DOM-Purify. DOM-Purify is a specialized library that detects and removes XSS attacks from HTML while preserving safe HTML tags. There are alternatives like Sanitize HTML or the XSS library, but DOM-Purify is widely used and well-maintained. In our example, the user input contains both a heading tag and a script tag. This demonstrates malicious use of HTML where someone tries to inject a script alongside legitimate formatting. After sanitization, we get just the heading tag. The script tag has been removed. For Markdown sanitization, we first parse the Markdown into HTML using the marked library, then sanitize the resulting HTML with DOM-Purify. So the user can write, for example, hello world in Markdown with a script tag, but the sanitizer removes the dangerous parts while keeping the safe formatting. This is different from validation because we are not rejecting the input. We are accepting it but transforming it to be safe. This gives users flexibility to format their content while protecting against attacks. And finally, let's look at escaping. This is probably the most important defense, and it's used in almost every application. The key principle here, you don't modify stored data. You encode it only at the moment of output to make it safe in its target context. Look at the first function, escape HTML. It takes a string and replaces special HTML characters with their safe equivalents. Why do we do this? Because these characters have special meaning in HTML. The ampersand symbol, for example, starts HTML entities. The less than symbol starts HTML tags. If we display these characters as is, the browser will interpret them as HTML code instead of text. So we convert them. Ampersand becomes the word ampersand amp semicolon. Less than becomes ampersand LT semicolon, and so on and so forth. Then when we use this in our HTML template, those special characters won't be interpreted as code. They will just display as the text characters the user typed. The second example shows SQL escaping using parameterized queries. We prepare a statement with a placeholder, then bind the user input to it. The database driver handles the escaping automatically. This prevents SQL injection, but we will talk about this type of attack later. Here's what you need to understand. Escaping happens at the last possible moment, right before the data enters a new context. When you are displaying data in HTML, you escape for HTML. When you are putting data in a SQL query, you escape for SQL. When you are inserting data into JavaScript, you escape for JavaScript. Each context has different special characters that need escaping. This is safer than escaping too early. If you escape data when storing it, you might later need to use the data in a different context that requires different escaping. By escaping at output time, you always use the right escaping for the context where the data is going. The first line of defense is client-side and server-side validation. For validation, you want three things. First, a length limit. This won't stop XSS directly, but it prevents attackers from injecting massive amounts of code. Second, a character whitelist if possible. For many applications, this rule will be too restrictive. If you're building a common system for a coding forum, users need to be able to type angle brackets. But if you're building a name field, you can restrict it to letters and spaces. Third, at minimum, reject obvious HTML tags. Look for patterns like script tags, iframe tags, JavaScript protocols in URLs. Now, if you are also using sanitization or escaping, this validation step isn't strictly necessary. Those techniques will handle the malicious content. But if you're only doing validation and nothing else, rejecting HTML tags can help prevent XSS. Now, here's the thing about validation. It's a good first step, but it's not enough. Regex pattern can be bypassed. Clever attackers find ways around character restrictions, so we need more defense layers. Also, the character whitelist approach has some serious limitation. First, it's too restrictive for international users. For example, if you only allow from A to Z and basic punctuations, what about users with names that includes accents, umlauts, or characters from non-Latin alphabets? You're basically excluding a large portion of the world. Second, users often need some formatting. They want to make text bold and italic, include links to sources. If you strip out all HTML, you remove legitimate use cases. Third, regular expressions can be exploited through red DOS attacks. That stands for regular expression denial of service. The example shows a regex with nested quantifiers. If someone sends input with many repeated A characters followed by a C characters, the regex engine can take exponentially longer to process it as the input grows. This can actually crash your server or make it unresponsive. So, while character whitelist seems like a good idea, they often don't work well in practice. This brings us to better defense. Sanitization on storage when HTML or Markdown is needed. If users need to include formatting in their input, you should sanitize it when displaying it, not when storing it. Store the raw, unsanitized data in the database. This way, you keep the original data. If you need to change your sanitization rules later, you can re-sanitize. Different contexts might also need different sanitization levels. For example, when displaying a comment, if you must allow some HTML, like bold, italic, and links, you configure DOM Purify with exactly which tags and attributes are allowed. You specify allowed tags, BI, EM, strong, etc. You specify allowed attributes, and you can even specify allowed URI schemes. In this example, only HTTP and HTTPS links. Then you can call DOM Purify Sanitize with these options before displaying the content for users. Now, there is an optimization you can do. You can store both the raw data and the sanitized version in two separate database fields. This way, you don't need to sanitize it on every read. You can just serve the pre-sanitized version, but you have to update both fields whenever the user edits their content. This is a trade-off: better read performance, but more complexity and storage. There are alternatives to DOM Purify. You can use, for example, Sanitize HTML or the XSS library. But DOM Purify is widely used and well-maintained, so it's a good default choice. Also, if you're allowing HTML or Markdown, you need a proper sanitization library. Don't try to write your own. There are tons of edge cases that you can miss. Different browsers interpret HTML differently, there are countless ways to encode malicious scripts, and new attack vectors are discovered regularly. Now let's talk about safe rendering. This is your last line of defense. It's what protects you even if validation and sanitization somehow fail or are bypassed. It's the final check that happens right when content is being displayed to users. The good news is that modern frameworks like React, Vue, and Svelte escape text automatically. When you write text in curly braces in React, React automatically escapes it. So even if someone managed to get a script tag into your database, it would be rendered as the literal text on the page, not executed as a code. The second point, avoid using tools like dangerously set inner HTML unless you're 100% certain the HTML is sanitized or escaped. The name is not a joke. It really is dangerous. When you use dangerously set inner HTML, you're bypassing the framework's default protection. You're telling React, I know what I'm doing, render this HTML exactly as is. The problem is, if you're wrong, if the HTML isn't actually sanitized, you have XSS vulnerability. And the vulnerability is your fault for using this method with untrusted data. The third option is to use text content instead of inner HTML when working with vanilla JavaScript. Text content treats everything as plain text, so even malicious script tags will just display as text characters. Now, let me walk you through what a secure write operation looks like when a user submits data to your server or changes anything. The flow starts with user interaction. The user types something into a form or click a button to do something. That goes to client-side validation, which is optional but recommended. Why is it optional? Because it's for user experience, it's not for security. Client-side validation shows errors in the interface before the user even sends the request to the server. This is convenient for users. They know the input is invalid earlier, and it prevents sending wrong payloads to the server that would just get rejected anyway. If client-side validation is successful, we send data to the server. Always send data via HTTPS to prevent man-in-the-middle attacks. This is important because if we do validation on the client side, a hacker can intercept and change the data during this transmission, and the server would receive malicious data. That's why validation only on the client is not enough, which brings us to the next step. On the server side, validation is mandatory. Never trust the client. All input must be validated on the server side, even if you validated it on the client side. Why? Because an attacker can bypass your client-side validation entirely. They can use curl or postman to send requests directly to your server, skipping your JavaScript validation completely. If server-side validation fails, throw a validation error. Server-side sanitization is optional. You only sanitize if you're allowing formatting or users can put raw HTML. If you decide to sanitize, here's what's important. Always save the sanitized data together with the original data. Never replace the raw data. I mentioned it before, but this is the important one, so I wanted to repeat it again. You might need the original data later for different contexts, or future security patches might improve sanitization. If you only saved the sanitized version, you have lost the original user intent. But if you're not allowing HTML formatting, you don't need sanitization at all. Just save the raw data to the database. You can handle safety through escaping when you display the data. So, to summarize, client-side validation is needed first of all to show errors in the UX for users' convenience and to prevent sending wrong payloads to the server. 2. Always send data via HTTPS to prevent man-in-the-middle attacks. 3. Never trust the client. All inputs must be validated on the server side. And 4. If you need to support formatting or users can put raw HTML, you can sanitize data on the server side using DOM Purify before storing it. If you do sanitize, save both, the sanitized version and the raw data. If you don't allow formatting, reject special characters in validation and save only raw data. Now let's look at the read operation, when your application fetches data from the server and displays it. The first question you need to ask, is it necessary to format this data? Are you working with a text editor or Markdown, where users need bold text, links, headings? Or is it just plain text, like the username or a comment without formatting? This decision determines your entire security strategy. If the answer is no, you don't need formatting, then just insert the data as plain text via text content or any other safe method. When you use text content in vanilla JavaScript or just display text in curly braces in React, the browser will escape it automatically. So even if the data contains script tags, they will be displayed as a literal text, not executed as code. If the answer is yes, and you do need formatting, then you must do client-side sanitization. And this is mandatory even if sanitization was already done on the backend before. There are two security strategies here. For plain text, use safe APIs like text content or React JSX. The browser escapes automatically, so you don't need to do anything special. For formatted HTML, sanitize with DOM Purify before rendering. You should call DOM Purify sanitize on the data right before you insert it into the DOM. Why is client-side sanitization mandatory for formatted content? Why can't we just trust that the backend already sanitized it? There are 4 reasons. First, corrupted database. If an attacker successfully performed SQL injection, they could have inserted malicious content directly in your database. Second, third-party API data. Your backend might be aggregating data from external APIs. Those external APIs may return unsanitized content. You can't control what they send you. And third, legacy data. This is all data from before you implemented proper sanitization. Maybe you built your app years ago and now you are improving security. All that old data is still in your database. Fourth, man-in-the-middle attack. If someone is intercepting your traffic on public Wi-Fi, they could modify the response before it reaches the client. This is why HTTPS is so important. So for formatted content, always sanitize on the client side before rendering, regardless of what the backend did. These protect you against all these scenarios. Let me give you clear guidelines on when to use each technique. Let's start with validation. You should validate as early as possible. Do lightweight validation on the client side for good user experience. This gives users instant feedback, but always revalidate on the server before writing to the database. These help catch errors early and prevents bad data from being stored in the first place. For escaping or parameterize right before rendering or sending data into another context, whether that's the DOM for HTML or the database for SQL. The main point here is that escaping too early risks data corruption. You might escape something for HTML, store it, then later need to use it in JSON API, where that escaping is wrong. The closer to output you escape, the safer and more predictable your app becomes. Use parameterized queries for SQL to handle these automatically. For sanitization, sanitize data rarely, only when users can include markup like HTML or Markdown. Here's when you use sanitization versus escaping. If users need rich formatting like bold text, links, headings, you need sanitization to allow safe HTML while removing dangerous HTML. If users are just typing plain text, like names, titles, descriptions, you don't need sanitization at all. Just use escaping when displaying. This technique is needed only for features like rich text editors, comments with formatting, or Markdown rendering. The best practice is to sanitize as close to the output as possible at render time. That's why client-side sanitization is mandatory for formatted content before inserting it into the DOM, because we might receive corrupted data from the backend. The pattern here is validate early, escape late, sanitize only for rich content. Before we move to the next topic, let's make a step back and discuss again why we want to store original, not sanitized data. Here are 5 reasons. First, you can't fix what you have destroyed. If you over-sanitize and remove something that was actually legitimate, you have lost that data forever. The user's original input is gone. Second, context changes. Maybe today you're displaying this data in HTML, so you sanitize it for HTML. But next year you want to export it to PDF or show it in a mobile app or send it through an email. The sanitization rules for each context are different. If you sanitized for HTML and stored that, now you have HTML escaped text in context where it doesn't make sense. Third, security patches becomes easier. Imagine DOM Purify releases a new version that catches attacks the old version missed. If you stored raw data, you can resanitize everything with the new version. If you sanitized on write, you're stuck with the old, potentially vulnerable sanitization. Fourth, if you need to integrate with other systems, they probably want the original data, not your application-specific sanitized version. And fifth, preserve user intent. Users type what they mean. If you modify it before storing, you might change their intended meaning. So the best practice is store raw data, sanitize at read time or render time. This gives you maximum flexibility and the best security over time. Now let's talk about Content Security Policy or CSP. Content Security Policy is an HTTP header that tells the browser what resources are allowed to load and execute on the web page. Think of it as a whitelist for your website. You specify things like which scripts we can run, where images can load from, which style sheets are allowed, and where the page can make network requests to. So you can see how this protects us from XSS. Even if an attacker injects malicious code into your page, CSP can prevent it from executing. The code example shows a common CSP setup. You're allowing CDN scripts, so scripts from your own domain can run. Allowing styles from your domain and from Google Fonts. You're allowing fonts from the Google Fonts CDN as well. But inline scripts are blocked, and any internal domains that aren't explicitly listed also blocked. This is powerful because even if an attacker manages to inject a script tag into your page through XSS, the CSP will block it from executing. The browser simply won't run the script that aren't from your approved domains. This works as a safety net even when other defenses fail. Alright, let's talk about a different type of XSS attack, which is called reflected XSS. This works differently from stored type. Here's the flow. Step 1. An attacker sends a phishing email with a link containing JavaScript code in a query parameter. The URL looks like a normal bank website, but the query parameter contains a malicious script tag. Step 2. When the victim clicks the link, their browser sends a request to mybank.com with the malicious payload in the query parameter. Step 3. The server receives the request and, without proper validation, reflects the malicious script back in its response. The server might say something like, "Your query is not a valid value," and include the actual query value in the message. Step 4. The victim's browser receives the response and executes the malicious script. Why? Because it came from the trusted mybank.com, the browser doesn't know it was originally from the attacker. The key difference from stored XSS is that this isn't saved in a database. It's reflected immediately back to the user. That's why it's called reflected XSS. The defense for reflected XSS are similar to stored one. First, properly escape all user input before rendering it. If you're going to display a query parameter value in an error message, escape it first. Second, use Content Security Policy. Even if you accidentally display an escaped input, CSP will prevent the script from executing. Third, never use inner HTML with untrusted data. This applies to all types of XSS, not just reflected. The pattern is basically the same. Don't trust any input and always escape before output or use safe rendering methods. Now let's look at the third type of XSS, which is called DOM-based XSS. This one is tricky because it's entirely client-side. Let's look at the image. Step 1. The attacker sends a phishing email with a malicious link. The malicious code is in the fragment, the part after the hash symbol in the URL. So the URL has a search parameter in the hash that contains an image tag with a malicious on-error handler. Here's what makes this different from reflected XSS. The fragment is never sent to the server. It only exists in the browser. When user clicks this link, the server just sees a request to the main page. The server has no idea about the malicious fragment. Step 2. The victim clicks the link and loads the page. The server sends back a normal safe page. Step 3. But the vulnerable JavaScript code on that page reads the URL fragment and directly inserts it into the DOM. The code does something like inner HTML equals location hash, which takes whatever is after the hash and puts it directly into the page. And that's when the attack executes. The browser runs the on-error handler from the injected image tag. Notice the search parameter is in the URL fragment. The fragment is never sent to the server, it only exists in the browser. Let's look closer at this type of attack. Here's an example. The vulnerable code listens for the DOM content loaded event. When the page loads, it reads from the URL hash using window location hash, which gets everything after the hash symbol. Then it writes that directly to the DOM using inner HTML. This is the vulnerability, writing directly to the DOM without escaping or sanitizing. So what happens? The browser loads the page, so nothing malicious yet. JavaScript reads the hash, which contains an image tag with a malicious on-error handler. Then JavaScript writes to the DOM using inner HTML, which is, as you remember, is dangerous method. And this is inserting that malicious content into the page. The browser executes the on-error handler because the image source is invalid. At this point, the cookie is stolen. The attacker now has the user session. DOM-based XSS is invisible to the server, which means it's harder to detect. Your server logs won't show anything suspicious because the attacker never touched the server. It all happens in the browser. The defenses for DOM-based XSS are the same as the other types. Properly escape all user input before rendering it, or sanitize. If you're reading from location hash or location search or any other user-controlled input, escape or sanitize it before putting it into the DOM via dangerous methods like inner HTML. Ideally, do not use it. Also, use content security policy to block inline scripts. Never use inner HTML with untrusted data. Use text content instead, or use a framework that escapes automatically. The pattern is consistent across all XSS types. Next, let me explain CSP or Content Security Policy in more depth because it's a critical defense mechanism. The main point is this. Even when an attacker can inject HTML or JavaScript into your site, CSP blocks the payload, allowing only certain whitelisted domain or resources to load. In other words, even if all your other defenses fail, if an attacker gets past your validation, past your sanitization, past your escaping, they will still be unable to run a malicious script on the page if CSP is configured correctly. Think of CSP as a permission list for what can execute, load, or run on your page. When CSP is active, inline scripts are blocked by default unless you explicitly allow them. The code shows different CSP configuration. The first example blocks everything. Scripts, images, styles, everything defaults to none. The second example allows only your domain, default src self. Only resources from your own domain can load. The third example is more practical. It allows your domain plus some other specific domains. Scripts can come from your domain or the CDN JavaScript net. Images can come from your domain. Styles can come from your domain or from specific CDN URLs. So CSP acts as a safety net. It's not your only defense, but it's a powerful last resort when everything else fails. Now, how do you actually set up CSP? Delivering CSP via HTTP header is the preferred way. You have two main options here. Option 1. Configure it at the server level. If you're using Nginx or Apache, you add the CSP header in your server configuration. Option 2. Configure it at the CDN level using services like CloudFront or Cloudflare. This is convenient because you can manage it without touching your server config. And also you can use HTML meta tags, but try to avoid this approach for several reasons. First, you can't use report URI with meta tags. Report URI is the CSP feature that sends your reports when CSP blocks something, which is really useful for debugging. Second, you can't use frame ancestor with meta tags. Frame ancestors prevents your site from being embedded in iframes, which protects against click-jacking attacks. Third, meta tags are less secure than HTTP headers. Headers are harder for attackers to manipulate, so HTTP headers are the way to go. Now you might think that CSP solves all our security problems. Unfortunately, that's not true. Relying only on CSP is not the best strategy. Here are the limitations. First, CSP can be bypassed in some cases. If you allow a CDN that an attacker can upload to, or if you have a permissive policy, attackers might find ways around it. Second, not all browsers support CSP currently, especially older browsers, so you can't depend on it for 100% of the users. Third, CSP can only protect against XSS. It doesn't protect against CSRF, SQL Injection, or other attack types. Fourth, CSP can be misconfigured on the server side. If someone sets up a permissive policy that unsafe inline or unsafe eval, the protection is weakened. So CSP is a powerful tool, but it's one layer in a multi-layer defense. You still need validation, sanitization, and escaping. Now let's talk about third-party scripts, because these create unique security challenges. Why do we need third-party scripts in the first place? Analytic tools like Google Analytics track user behavior, page views, and conversions. Payment processors like Stripe accept credit cards securely. Chat support widgets provide live chat with customers. Map from Google or Mapbox show locations. These are legitimate business needs. But here's the problem. They get hacked. If the third-party service is compromised, every website using this script is compromised too. They might load additional scripts that you didn't know about. And if those additional scripts are compromised, that creates a supply chain attack where the attack comes through a trusted dependency rather than directly targeting you. So every third-party script you add is a potential security risk. Let me explain what a supply chain attack actually looks like. The main thing to understand, the attacker hacks something you trust, not you directly. Here's an example. Your app includes a script tag pointing to analytics.com. You trust this domain because it's a legitimate analytics service. Step 1. An attacker hacks analytics.com and modifies track.js to include malicious code. They might inject code that steals cookies or credit card numbers, for example. Step 2. Your website loads this malicious code automatically. From your application perspective, nothing changed. You're still loading the same track.js file, like you always did. But now that script contains malicious code. Your users get hacked, and you might not even know it happened. The attack came through a trusted third party, not through a vulnerability in your own code. This is why supply chain attack is so dangerous. You can have perfect security in your own code, but if a third party you depend on gets compromised, you are compromised too. Now, how do you defend against it? You can use sub-resource integrity to ensure scripts haven't been modified. You can use CSP to limit what third-party scripts can do. The best defense, if you can, is to minimize the number of third-party scripts you use. Every script is a risk. You should also use security scanning tools like GitHub Security, SonarQube to monitor your dependencies and detect known vulnerabilities in the third-party packages. Alright, that covers client-side security. We learned about the 3 types of XSS attacks. Stored XSS, where malicious scripts are saved in your database and affects all users. Reflected XSS, where the attacks come through URL parameters and is reflected back immediately. And DOM-based XSS, where the attack happens entirely in the browser without the server ever seeing it. We covered 3 key techniques and when to use each one. Validation to check if input is correct according to business rules. Sanitization for when users need rich formatting, like bold text and links. And remember, client-side sanitization is mandatory before rendering formatted content. Escaping for safely displaying any data at output time. The pattern is validate early, escape late, sanitize only for rich content. We discussed why you should store raw original data in your database rather than sanitized data. Because context change and security tools improve over time. We learned about content security policy as a safety net that blocks malicious scripts even when other defenses fail. And we covered the risks of third-party scripts and supply chain attacks. Every script you add is a potential security issue, and you should use tools like GitHub Security or SonarQube to monitor these dependencies. Now let's talk about security in transition, the security of data as it moves between the client and the backend. Let's start with the most common attack on data in transition, the man-in-the-middle attack. The basic idea is simple. A hacker positions themselves between you and the server, intercepting everything. Here's how it works in practice. First, a hacker creates a fake Wi-Fi point or hack into a router. Maybe they set up a network called Starbucks free Wi-Fi or something like that in a coffee shop. A user sees this network, thinks it's the real Starbucks Wi-Fi and connects to it. Now all the user's traffic goes through the hacker's device. Every request the user makes, every response they receive, the hacker can see all of it. The hacker forwards the original request to the server. So from the server's perspective, everything looks normal. The request arrives, it's processed, nothing seems suspicious. The server responds normally. It sends back the data the user requested. And now the hacker can read the response. They can see everything: passwords, session cookies, credit card numbers, API keys, and personal information. And here's what makes this attack so effective. The user has no idea it's happening. The website loads normally, everything works, but the attacker is silently recording everything. What are hackers looking for? Passwords, obviously. Those give direct access to accounts. Session cookies, which let them impersonate you without knowing your password. Credit card numbers for financial theft. API keys and tokens that grant access for services. And personal information that can be used for identity theft or sold on the dark web. This brings us to HTTPS, which is the main defense against man-in-the-middle attacks. Let me start with the core problem. In a regular HTTP connection, all data travels in plain text. That means if you type your password and send it over HTTP, anyone intercepting the traffic can read it directly. It's like sending a postcard through an email. Anyone who handles it can also read what's written. How does HTTPS solve this? The client and server establish an encrypted connection using asymmetric cryptography. Asymmetric cryptography means that there are two keys: a public key that anyone can use to encrypt data, and a private key that only the server has to decrypt it. During the initial handshake, these keys are used to securely agree on a shared secret. Then, all subsequent data is encrypted with symmetric encryption. Symmetric encryption is faster than asymmetric. It uses the same key to encrypt and decrypt. Now both the server and the client have this shared secret key, and they use it to encrypt every piece of data they send. Even if an attacker intercepts the message, they can't read it. It's just meaningless encrypted bytes without the decryption key. Now you might think, what if a user types HTTP in the URL bar? We should just redirect them to HTTPS and problem solved. That's better than nothing, but redirect alone is not enough. And here's why. The first HTTP request is unencrypted. Before the redirect happens, the user has already sent an HTTP request in plain text. An attacker can intercept that first request, see what the user is trying to access, and potentially modify it or steal information from it. The solution is HSTS, which stands for HTTP Strict Transport Security. Here's how it works. The server tells the browser, always, use HTTPS for my domain. This is communicated through a special header called Strict Transport Security. The browser remembers this instruction for a specified period of time. And crucially, future requests skip HTTP entirely. The browser automatically uses HTTPS without even attempting HTTP first. So even if the user types HTTP in the address bar or clicks an HTTP link, the browser knows to upgrade it to HTTPS before sending any request. You might be wondering, why should we use HTTPS even for public content? If the data isn't sensitive, why bother encrypting it? There are three main reasons. First, HTTPS prevents tampering. Tampering means someone modifies the content as it travels across the network. Without HTTPS, anyone between you and the user can inject ads or malicious code into your pages. Attackers on public Wi-Fi can inject malware. HTTPS prevents all of this because any modification to the encrypted content would break the decryption. Second, modern features are required. Service workers, progressive web apps, geolocation, camera access, browsers block all of these features on HTTP sites. If you want to use any modern web platform capabilities, you must use HTTPS. Trust and SEO. Browser shows a not secure warning on HTTP sites, which damages user trust. And Google penalizes HTTP sites in search ranking, so you will rank lower than HTTP competitors. So the bottom line is, even if your content is publicly available and not sensitive, you still need HTTPS. Let me give you some best practices for implementing HTTPS. First, enforce HTTPS everywhere. Redirect all HTTP traffic to HTTPS using a permanent redirect at the server level. This is called a 301 redirect. It tells browsers and search engines that the HTTP version no longer exists and they should use HTTPS instead. Never serve sensitive operations over HTTP, not even temporarily. The next one is implement HSTS. Use the strict transport security header. This tells browsers to always use HTTPS for your domain. Set a long max H value, like for example 1 year. Remember, HSTS prevents that first unencrypted HTTP request. The browser will automatically use HTTPS even if the user types HTTP in the address bar. Proper certificate management. Use certificates from trusted certificate authorities. Don't use self-signed certificates in production. Automate renewal with tools like Let's Encrypt. This is free and handles renewals automatically, so your certificates never expire. Use modern TLS protocols. Disable TLS 1.0 and 1.1, which have known vulnerabilities. Use TLS 1.2 minimum, but TLS 1.3 is preferred because it's faster and more secure. Secure cookie configuration. Set the secure flag on all cookies so they only transmit over HTTPS. Combine this with HTTP only, which prevents XSS attacks from reading cookies, and SameSite, which mitigates XSRF attacks. We will talk more about SameSite attribute when we get to XSRF. Now, let's talk about CORS, which stands for Cross-Origin Resource Sharing. CORS is a security feature in browsers that controls whether JavaScript on one website can make requests to a server on a different domain. Why is it needed? It prevents malicious websites from making requests on your behalf to servers where you are authenticated. Without CORS, if you're logged into your bank in one tab, a malicious site in another tab could send requests to your bank's API using your session, and the browser would automatically include your authentication cookies with those requests. Let me explain how CORS works. The browser checks if a cross-origin request is allowed. When your JavaScript tries to fetch data from a different domain, the browser doesn't just send the request. It first checks if this is allowed. The server responds with special headers saying yes or no. The server sends back headers like access control allow origin to declare its policy. The browser enforces this decision. If the server says yes, the browser allows your JavaScript to access the response. If the server says no, the browser blocks it. Here's an example. Your siteapp.com wants to call an API at apiexample.com. Without CORS headers from apiexample.com, the browser blocks the request. With proper CORS headers, the browser allows it. The main thing to understand here, the CORS check is initiated by the browser, and the browser blocks the response or request. The backend only sends headers like access control, allow origin to declare its policy, and the browser enforces it. Let me clarify what this means for us. Your backend can't protect itself with CORS. CORS is enforced on the client side in the browser. The request might still reach your server, but the browser prevents the malicious JavaScript from reading the response. So CORS protects your users from malicious websites trying to abuse their authenticated sessions. It is a browser security feature, not a server security feature. If someone is using Postman or curl, for example, instead of the browser, CORS doesn't apply at all because there is no browser to enforce it. And in those tools, it's actually not needed, since there are no cookies being sent automatically with requests. Now, in the CORS specification, we have simple and complex requests. Let me explain the difference. Simple requests are low risk. GET requests, POST requests, but only via HTML forms, images, iframes, these are all considered simple. Technically, all these requests can delete data, but if your API is implemented properly, they shouldn't. GET should only read, POST via forms should be safe operations. Complex requests are higher risk. This includes delete or put requests that can destroy data. Also, any request with custom headers like authorization tokens, or any request made with fetch or XML HTTP request APIs. Now, here's an interesting thing. CORS does not apply to classic HTML forms, posts, requests. The web platform intentionally grandfathered them in for backward compatibility long before CORS existed. So if you submit a form the old-fashioned way with a form element and a submit button, CORS doesn't block it even across origins. If a request is not allowed by CORS, it will be blocked, whether simple or complex. But here's the important difference. Simple requests reach the backend and execute, but the response is blocked by the browser. So if you make a GET request that's not allowed by CORS, the server processes it and sends back the response. But the browser blocks your JavaScript from seeing that response. Complex requests never reach the backend. They are blocked before execution. The browser sends an option pre-flight request first. If that's forbidden, the actual request is never sent. This is why complex requests are safer for destructive operations. A delete request that's not allowed by CORS won't even reach your server. The pre-flight fails and nothing happens. Let me explain how this pre-flight mechanism works for complex requests. Phase 1 is the pre-flight request itself. The browser automatically sends an options request to the server. This request asks the server if the intended HTTP method and custom headers are allowed. For example, if you are about to send a POST request with a custom authorization header, the options request asks, "Can I send POST? Can I include these authorization headers?" The server responds with a 200 code and specific CORS headers granting or denying permission. Phase 2 is the actual request. The browser proceeds only if permissions were granted in the pre-flight response. The client sends the final intended request, for example, the POST with the actual data. The server executes the business logic and returns the final response. Here are some best practices for CORS configuration. Whitelist specific origins on the server. Never use the wildcard asterisk with credentials. That's a security hole. Specify exactly which domains are allowed. Specify exact methods. List only the HTTP methods you actually support, like GET, POST, PUT, and delete, for example. Specify exact headers. List only the headers you need, for example, content type and authorization. Set pre-flight cache. Use max age of 24 hours. This tells the browser it can cache the pre-flight response, reducing the number of options requests. And use a CORS library. Don't write CORS headers manually. It's easy to forget headers on some roads or to forget to handle options for every road. Use your framework's CORS middleware. It handles all of these automatically. Now let's talk about CSRF, which stands for Cross-Site Request Forgery. An attacker tricks a user into making requests to a site where they are logged in. The key thing to understand is that the attacker doesn't steal your password or session. Instead, they make your browser send requests using your existing logged-in session. And here's something that confuses people. CORS is not protecting us from CSRF. Let me explain the difference. CORS prevents malicious sites from silently reading sensitive responses, such as API data or user info, from other origins where the user is authenticated. It is about blocking access to response data. CSRF is an attack where a malicious website uses a user's logged-in session on another site to perform actions the user didn't intend. It's about preventing forget actions, not about reading data. Let me walk you through a CSRF attack step by step. Step 1. A hacker sends a fake email to trick the victim into clicking a link. Maybe it says something like, "You want money," or "click here to claim your prize." Step 2. The victim clicks the link and opens the hacker's website. And crucially, the victim is still logged into their bank in another tab. Step 3. The malicious site after submit a hidden form to bank.com. The browser automatically sends the victim's cookies with the request. This is the main thing. Your browser automatically sends cookies to a domain whenever you make a request to that domain, regardless of which website triggered the request. Step 4. The bank receives the request, sees valid cookies, and thinks the user is authorized, and processes the money transfer. The victim had no idea this happened. They clicked a link, a page loaded, nothing looked suspicious. But in the background, the malicious site submitted a form on their behalf. There are 4 main defenses against CSRF. The first one is CSRF token. The server generates a random token and includes it into form. The attacker can't know this token, so they can't forge a valid request. The important thing here is that unlike cookies, this token is not sent automatically by the browser. Your code has to explicitly include it. This is why it works as a defense. Number 2. SameSite Cookies. This is the modern defense against CSRF. The browser won't send cookies with cross-site requests. So even if a malicious site tries to submit a form to your bank, the authentication cookie won't be included. 3. Check origin or referrer headers. The server checks where the request came from. If it's coming from a malicious site instead of your own site, it will reject it. And 4. Require authentication for sensitive actions. For things like transfers or password changes, ask for the password again before allowing the action. Let me explain the CSRF token defense in detail. This is the same attack scenario as before, but now we are using CSRF token as a defense. Step 1. The user logs into bank.com with email and password, receiving authentication cookies and also CSRF token. The token is unique and unpredictable. Step 2. An attacker sends a phishing email to the user and user clicks the malicious link. Step 3. The malicious site automatically submits a hidden form to transfer money to the hacker's account. Step 4. The browser sends cookies automatically, but the attacker can't know the CSRF token because it's not stored in a cookie. It's in the HTML or in JavaScript memory, so the request is rejected. This is how CSRF token works. The attacker can treat your page to steal the token, and they can guess it because it's a large random value. For CSRF tokens to be effective, they need to meet certain requirements. The token must be unique per user session. 2 different users should never have the same token. It must be secret and unpredictable, a large random value that can't be guessed. It must be generated server-side, not client-side. The server creates it and includes it in the page. And here you have a choice: 1 token per session or 1 token per request. Unique token per request is more secure. Every form submission requires a fresh token. But this creates usability issues. For example, if a user opens multiple tabs and submit forms in different orders, all their tokens might be invalidated. And the second option is unique token per session, which has a better user experience. The same token works for the entire session, but it's less secure. If the token leaks somehow, it's valid for longer. Most applications use per session tokens for the better user experience. There are several ways to store and transmit CSRF tokens. How to transmit the token? 2 main approaches. 1. Hidden form field. You include it as a hidden input in your HTML form. When the form is submitted, the token goes in the request body. And 2. Custom header. You send it in a custom HTML header like XSS token. This is more secure and works better with Fetch API. Where to store the token? We have 4 options. First, hidden form field. Simple and works with traditional forms. 2. Cookie with the double submit pattern. You store the token in a non-HTTP only cookie and also send it in a custom header. The server compares them. 3. Meta tag. You put it in an HTML meta tag and read it with JavaScript. 4. JavaScript memory. You store it in a JavaScript variable and include it in the fetch requests. There are 2 main approaches to validating CSRF tokens: stateful and stateless. Stateful using hidden form field. the token is integrated into the HTML. The server stores it in the session or database. When you submit a form, the token comes in the request body. The server compares, is the token from the client equal to the token in the database? This requires server state because you are tracking token in a session. And the second one is stateless using cookies. The token is stored in both a non-HTTP only cookie and sent in a custom header. When the request comes in, the server compares, is the token from the header equal to the token from the cookie? This requires no server state because you're just comparing two values that both came from the client. The security comes from the fact that attackers can't read cookies from other domains to include them in custom headers. Let me compare these four approaches. The first one is hidden form field. Token stored in HTML, sent in the request body, requires server state. This is stateful approach. It is not suitable for fetch calls with JSON payloads because the token needs to be in the HTML form. The second one, cookies with double submit. Token stored in a non-HTTP only cookie, sent in a custom header, and requires no server state. This is stateless approach. But it is vulnerable to XSS because the token cookie must not be marked HTTP only. Your JavaScript needs to read it. Meta tag. Token stored in an HTML meta tag, sent in a custom header, requires server state. It's vulnerable to XSS because JavaScript can read the meta tag. Also, it requires maintaining a session on the server. And JavaScript memory. Token stored in a JavaScript variable, sent in a custom header, requires server state. Vulnerable to XSS because the token is in JavaScript memory and also requires maintaining a session on the server. The main trade-off here, stateful approaches like hidden form field are not vulnerable to XSS because require server-side session storage. Stateless approaches like the cookie method don't require sessions but are vulnerable to XSS. Now let's talk about SameSite Cookies, which is a simpler defense than CSRF tokens. SameSite is the rule you put on cookies that tells the browser, only send these cookies when the user is on my website. Don't send it when they are on some other website trying to access me. There are three possible settings for the SameSite parameter. Strict gives maximum security but less convenience. The browser never sends the cookie to your site from another site, even if someone just clicks a normal link. This breaks things like, for example, email link to your site because the user won't be logged in when they click the link. The next one is lax, is balanced and recommended. The browser sends the cookie when someone clicks a normal link from another site, but it blocks sending the cookie on dangerous requests like post, put, delete from other sites. This is the best compromise for most applications. And none is least secure. The browser always sends the cookie everywhere. Only use this if you absolutely need cross-site cookies, like for embedding content, for example. Lax is recommended for most applications. Another defense is checking the origin and refer headers. The strategy is simple. Check where the request is coming from. Look at the origin or refer headers. These are set automatically by the browser on every request. Check if your trusted domain list includes that origin. If the request is coming from apple.com, for example, trying to post to bank.com, you should reject it. Browsers set these headers automatically. Attackers can't fake them because they are controlled by the browser, not by JavaScript. But here's the catch. Sometimes these headers aren't present even in legitimate requests. Some browsers or privacy tools remove them, so you need a careful policy. Block only if headers are present but don't match. If headers are missing entirely, you will need to rely on other defenses like CSRF tokens or SameSite cookies. The fourth defense is reauthentication or out-of-band codes. Authentication requires password entry before sensitive actions. Before you can transfer money, you have to enter your password again. Out-of-band codes are verification codes sent through separate channels like SMS, email, Authenticator app. The server sends a code to your phone and you have to enter it to confirm the action. The pros, very strong security. This protects against multiple attack vectors, CSRF, session hijacking, XSS. An attacker might have your session cookies, but they don't have your password or access to your phone. The cons, bad UX. It interrupts user flow and feels annoying. It requires additional infrastructure like SMS gateway or email services. And it can have reliability issues, SMS interceptions, delivery failures, and phones without signal. Most applications reserve this for truly critical operations, like changing your email address or transferring large amounts of money. Now here's something important. Even if you use CSRF tokens but your application is not secure against XSS, those tokens won't help you. Let me explain how this combined attack works. Phase 1 is injection and theft. A hacker exploits a vulnerability to inject a malicious script onto the target's page. This is an XSS attack we covered in part 1. The execution script reads the valid CSRF token from the HTML. Since the script is running on the page, it has full access to the DOM and can read the token. Phase 2 is forgery. The victim clicks a malicious link or element, triggering the attack script. The script dynamically creates a new hidden form, inserts the stolen token, and includes the malicious payload. The browser submits the perfectly valid form, including the victim's session cookies and the correct stolen token. This is why defending against XSS is so important. If you have XSS vulnerabilities, CSRF tokens won't save you. The attacker can read the token and forge valid requests. This is also why some CSRF tokens approaches are more vulnerable to XSS than others. If your token is in a cookie that's not HTTP only, or in a meta tag, or in a JavaScript memory, XSS can easily steal it. The main takeaway: when you are protecting against CSRF, don't forget about XSS. You need to address XSS first. There is also something called client-side CSRF. Client-side CSRF is an attack where the hacker exploits a vulnerability in the website JavaScript code to trick it into building and sending a forget request to the server by manipulating an input like the URL. Let me give you an example. User gets tricked into clicking a malicious link, maybe through a fake email or message. The URL contains a malicious parameter that the site's JavaScript will read. The vulnerable JavaScript code reads this parameter from the URL and uses it to construct an API request. The code automatically includes the CSRF token because it's legitimate code running on your site. The browser sends the request with the authentication cookies. The vulnerability here is that your JavaScript is blindly trusting URL parameters and using them to construct API requests. The attacker didn't inject a script, they just manipulated the URL to make your own code do something malicious. The defense is to be careful with how you use URL parameters. It is fine to use them for filters or search requests, things that only read data, but don't use user-controlled input from URLs to construct API endpoints for critical operations or requests that can change state, like put, post, and delete requests. Validate and sanitize URL parameters before using them for anything sensitive. Now, let me give you a decision framework for defending against CSRF. First question: does your application use cookies for authentication? If yes, your first line of defense is SameSite equals lax or strict. Your second line is to check origin and refer headers. Then ask, is this a single-page application or a multi-page application? For SPAs, use CSRF tokens with the double submit pattern or synchronizer token. Just to remind you, double submit means storing the token in a cookie and also sending it in a header, then comparing them on the server, which is stateless approach. The synchronizer token means storing the token on the server and validating it there. This is stateful approach. The double submit pattern works well with Fetch API. For MPAs with traditional forms, use CSRF tokens with the hidden form field approach. For critical operations like changing passwords or transferring money, you might add re-authentication or out-of-band codes as an extra layer of defense. If you are not using cookies for authentication, if you're using something like GWT in local storage, your CSRF attack risk is lower. But you should still validate origin and refer headers if it's possible. One critical note: defend against XSS first. XSS vulnerability can lead to CSRF. If attackers can inject scripts, they can steal tokens and bypass all your CSRF defenses. And there is one more thing. Corporate proxies and privacy tools sometimes strip origin and refer headers, so don't rely solely on these headers. Combine them with other defenses. Alright, That covers security in transition. Let me recap what we learned. We covered man-in-the-middle attacks and how hackers can intercept unencrypted traffic on networks. We learned why HTTPS is essential, not just for sensitive data but for all web applications. We discussed HSTS and how it prevents that first unencrypted request. We covered CORS, which is a browser security feature that controls cross-origin resource access. We learned about simple versus complex requests and per-flight requests. We covered CSRF attacks and the four main defenses: CSRF tokens, SameSite cookies, origin and refer header validation, and also reunification. We discussed the trade-offs between stateful and stateless token approaches and why lags is the recommended SameSite setting. And most importantly, when protecting against CSRF, think about XSS first. XSS can bypass your CSRF defenses. Now let's talk about security on the backend side. In part 1, we covered Frontend Security, how to protect against XSS attack. In part 2, we covered security in transition, HTTPS, CORS, and XSRF. Now we're moving to the backend. This is where your data lives, where your business logic runs, and where many of the most damaging attacks happen, if you are not careful, of course. The first and most important principle of backend security: never trust the client. Don't assume the data coming from the frontend is what you think it is. The client can be compromised in several ways, and we looked at some of them before. It could be hacked if there is an XSS vulnerability or malware on the user's machine. Attackers control what data gets sent to your server. It could be intercepted and altered through a man-in-the-middle attack. Even with HTTPS, if someone has compromised the user's device or network, they might modify requests. Or the user could be intentionally sending malicious data, like SQL injection attacks, credential stuffing, where they are trying thousands of stolen passwords, or any number of other attacks. Here's the thing: the browser is not a secure place. We don't control it. The network is also not secure, so the backend is our last line of defense. If everything else fails, the backend is what protects your data and your users. So what should you do? Validate everything server-side. Don't assume front-end validation worked. Someone could bypass your front-end entirely and send requests directly to your API using tools like Postman or curl. All validation must happen on the backend as well. Verify user identity. Get the user ID from the authentication session or JWT token, never from the request body. If your endpoint needs to know which user is making the request, extract that from the authentication mechanism, not from a parameter the client sends. Verify user permissions. Check on every endpoint whether this user has access to these resources. Just because someone is logged in doesn't mean they should be able to access, for example, another user's data or perform admin operations. This is called the principle of least privilege. Give users only the minimum access they need to do their job and nothing more. Recalculate sensitive values. Never trust prices, discounts, or totals from the client. If you're building an e-commerce site and the client sends you a cart with prices, recalculate those prices on the server. Attackers can easily modify client-side code to send different prices. One of the most common backend attacks is SQL injection. An attacker inserts malicious SQL code into user input. This happens when you build database queries using string concatenation with unvalidated user input. The vulnerability required three things: dynamic queries, string concatenation, and unvalidated user input. When all three are present, you have a SQL injection vulnerability. Let me explain how it works. The attacker injects malicious SQL code into a user input field like username or login field. Instead of typing a normal username, they type SQL commands. The server-side code uses string concatenation to build the database query. Think of it like this. Instead of using a safe approach that we will talk about in a moment, parameterized queries, which treat user input as a pure data, the server just takes whatever the user typed and drops it directly into the SQL query string. And here's the problem. The server thinks it's putting a username into the query. But what if the user didn't type a username? What if they typed actual SQL code? The server doesn't check. It just builds a string and executes it. So the database receives what looks like a valid SQL query, but it is actually the attacker's malicious code mixed with your intended query. The database has no way to tell the difference. It just executes everything as SQL. What can an attacker do with this? They can read any data from your database: customer information, passwords, credit card numbers. They can modify data, change prices, delete records. They can even execute administrative operations on the database server, creating new admin accounts, dropping entire tables, or taking over the database completely. All of this possible because the attacker's input is being executed as code instead of being treated as data. The primary defense against SQL injection is parameterized queries, also called prepared statements. Here's how it works. You define the SQL query structure first with placeholders, then pass user input separately as parameters. The database knows to treat the parameters as data, not as executable code. The pros: it is simple and works with all databases. This should be your default approach for all database queries. The cons: you can't use parameterized queries for dynamic SQL parts like table names or column names, for example. If you need to dynamically choose which table to query, you will need a different approach, like an allo list, for example. Other options for safe database access include ORMs like Prisma or Type ORM. These handle parameterization automatically. SQLize can work but requires careful use. It's easy to accidentally introduce SQL injection if you are not careful with raw queries. Another defense is stored procedures. A stored procedure is SQL code stored in the database itself, not in your application. Your app calls the procedure instead of writing queries. This provides database-level security. The SQL code is defined once and can be modified by application code. The cons: stored procedures are database-specific, meaning if you write them for MySQL, for example, they won't work in PostgreSQL. You would have to rewrite them. This reduces portability, the ability to switch databases easily. Debugging is harder because the code isn't in your application, and over time you can end up with too many stored procedures cluttering your database, making it harder to manage. Stored procedures are useful for complex operations that need to be tightly controlled, but parameterized queries are simpler for most cases. For dynamic parts of queries, like table names, use an allo list. Only allo-specific, pre-approved values from user input. Reject anything not on the list. The pros: it is simple, explicit, and easy to understand. When implemented correctly, it's very secure. The cons: you must maintain the allo list. It is easy to forget edge cases, and this approach doesn't work for values like usernames or amounts, only for things like table names, column names, or sort directions where you have a fixed set of valid options. Now let's talk about rate limiting. Rate limiting means you limit how many requests a user or IP address can make to your server in a time period. What does rate limiting prevent? Here are 4 examples. Brute force attacks on login or password guessing. Without rate limiting, an attacker can try thousands of passwords per second. API abuse and credential stuffing, where attackers use stolen credentials from other sites to try logging into your site. DDoS attacks, distributed denial of service attacks, where attackers flood your server with requests to take it offline. And resource protection. When too many requests hit your server at once, your database gets overloaded trying to process them all, your bandwidth gets consumed, your CPU goes out. Rate limiting prevents this by capping how many requests any single user can make. Rate limiting by itself slows attackers down, but it's not enough on its own. That's why it should be combined with other defenses to create layers of protection. For example, account lockout. After n failed login attempts, log the account for m minutes. This prevents attackers from continuously guessing passwords. CAPTCHA. After n failed attempts, require human verification. This stops automated attacks. Monitoring. When suspicious activity is detected, the security team gets alerted and can block the attacker manually. And MFA. Multi-factor authentication. Even if an attacker guesses the password through brute force, they still need the second factor. Without rate limiting, an attacker can make unlimited attempts. Let's say it takes 50 minutes on average to find a password by trying common passwords. With rate limiting, for example, max 5 attempts per 15 minutes. That same attack now takes around 3 years. So the attack becomes completely impractical. The attacker will give up and move to an either target. Let me explain how rate limiting works technically. This is just one way to implement it. A simplified example. Real implementation can be more sophisticated, but this gives you the basic idea. First, a client makes a request to the API. The rate limiter receives it first before it reaches your application. The rate limiter queries the cache or database to see how many requests this client has made in the last 60 seconds. The rate limiter itself is storing this count. Every time a request comes in, it increments a counter for that client and saves it to the cache or database. If the request count is within the limit, the request is forwarded to the API server for processing. If the limit is exceeded, the rate limiter rejects the request immediately. The API server never sees it. This example uses the fixed window approach, the simplest method. Here's how it works. Every 60 seconds, the counter for each client resets back to 0. So if a client makes 5 requests at second 59, their counter resets at second 60, and they can make 5 more requests. The window is fixed. It's always 1 to 60 seconds, then 60 to 120, and so on. There are more sophisticated approaches like sliding window or token bucket, but fixed window is the easiest to understand and implement. Let's talk about error handling. When something goes wrong on your backend, for example, a database error, a failed query, an exception in your code, how you communicate that error to your clients matters for security. You should respond with generic error messages. Don't give away too much information about what went wrong. Do not pass technical details to the client. Here are the things we shouldn't reveal. Never expose stack traces to the client. Stack traces reveal your code structure, file path, and implementation details. Never expose database details. Error messages shouldn't reveal your database type, table names, or schema. Never expose file path. These tell attackers about your server's directory structure. Never expose internal IP addresses. This tells attackers about your internal network, what other servers you have, how they connected, which services are running where. Now here's what you should do instead. Log everything internally for your debugging purposes. When an error happens, log all the details you need, like stack trace, database query, everything. But return generic messages to users. Something like, an error occurred, please try again later. The problem with exposing details is that it helps attackers. If they see a database error with table names and column names, they now know your database schema. That makes SQL injection much easier. Now let's talk about secure storage of sensitive data. Rule 0. The best security strategy is not to store sensitive data at all, especially things like credit card numbers. How can you not store what you need to store? For example, you can use third-party services. For credit cards, you can use payment processors like Stripe or PayPal. They handle the credit card data and you never see it. For social security numbers or sensitive documents, only store them if you absolutely must. If you don't store it, it can't be stolen. Rule 1. If you must store sensitive data, you must encrypt it. Use strong encryption standards like, for example, Advanced Encryption Standard. Rule 2. The encryption key, think of it as a master password, must be stored separately from the encrypted data. If an attacker steals the database, they get the encrypted data, but if the encryption key is stored somewhere else, they can't decrypt it. If they can steal both in one breach, the encryption is useless. And Rule 3. User passwords must not be stored using encryption. Use secure hashing algorithms instead. This is important enough that we will spend the rest of this section on it. The goal of secure password storage is to protect user passwords even if your database is compromised. We protect against offline brute force attacks. Password must be hashed, not encrypted, and this is crucial. Hashing is a one-way function. It is impossible to reverse a hash to get the original password. Once you hash it, it's gone forever. Encryption is a two-way function. The original data can be retrieved if you have the encryption key. This should almost never be used for passwords. Here's why encryption is dangerous for passwords. If hackers can steal the encryption key, they can decrypt all the passwords. That's why we must use hashing. With hashing, there is no key to steal. Let me explain how hashing works. Hashing is a one-way function that converts data into a fixed-length string. The same hash function always returns the same result for the same input. Here's the full picture of how this works in practice. When a user registers with a password, we hash it immediately and store only the hash in the database. We never store the actual password. When the user tries to log in later, they type the password again. We take what they typed, hash it using the same hash function, and compare the result to the stored hash in the database. If the hashes match, we know they typed the correct password. This consistency, the fact that the same input always produces the same hash, is what allows us to verify passwords without ever storing them. Let's compare what happens in a breach with encryption versus hashing. If a hacker steals both the encrypted passwords and the encryption key, they can decrypt everything and get the original passwords. This gives the attacker full access to all user accounts. They can log in as any user. And scenario 2, hashing. If a hacker steals hashed passwords, they can't do anything with them immediately because hashing is irreversible. There is no key to decrypt them. The passwords remain protected even after a database breach. But this doesn't mean hashed passwords are completely safe. Attackers can still try to crack them, which is what we'll discuss next. Hashing by itself is not enough because of 3 critical weaknesses. Rainbow tables. Attackers can build a massive pre-calculated list called a rainbow table. Where do they get these passwords? From lists of commonly used passwords, like for example password123, QWERTY, etc. These lists come from previous data breaches where millions of passwords were leaked. The attackers take these common passwords, hash each one, and store the results in a table. Once this table is built, cracking hashes is instant. They just look up your hash in the table, and the lookup operation is extremely fast, like searching a dictionary. 2. GPU brute force attacks. Let me explain how this works. Attackers have these stolen hashes from your database. They also have the same list of common passwords. They take each password, hash it, and compare the results to the stolen hashes. If they find a match, they have cracked the password. Graphics processing units are extremely good at performing the same simple hashing calculation billions of times per second. They can try every common password very quickly, millions of passwords in just hours. And the third weakness, collision attacks or lack of uniqueness. Remember, I said before that the same hash function always returns the same hash for the same input. This becomes a problem. If 2 users both have the password like password123, they will both have the exact same hash in the database. An attacker only needs to crack one password hash to get the password for every other user who used the same password. So if, for example, 100 users all have password123, cracking one gives you access to 100 accounts. The solution to these problems, or at least some of them, is salting. A salt is a random string. Here's how it works. When you hash a password, the hash function generates a random salt for that specific password and combines it with the password before hashing. The salt is then stored alongside the hash in your database. It is not a secret, it is visible in the stored hash, but it still provides protection. Here's what salting does to defend against attacks. Every password gets a different salt, even if the passwords are identical. So if 2 users both have password123 password, they will have completely different hashes because they have different salts. This prevents collision attacks. Attackers can't pre-compute all hashes because the salt is random. It means rainbow tables become useless because you would need a separate rainbow table for every possible salt, which is impossible. This prevents rainbow table attacks. And also salting makes cracking passwords much slower. When attackers try to crack a password with a rainbow table, they can't use the table anymore. They have to actually compute hashes each time. They take their list of common passwords and the salt they extracted from the stolen hash each guess with that salt and compare. This takes real computation time instead of instant lookups. To better understand how offline brute force attack works, Let me walk you through what an attacker would do after stealing hashed passwords. What the attacker has: stolen hashes from your database. These hashes have the salts stored right inside them, and a list of frequently used passwords. Here's the attack process. The attacker takes each password from their list and hashes it using the salt they extract from the stolen hash. Then, they compare the computed hash to the stolen hash to find matches. If the hashes match, they have found the password. This is why we need slow hashing algorithms to make this process as painful as possible for attackers. There are three main defenses against brute force attacks on stolen hashes. The first one is use slow hashing algorithms. This is the most important defense. What do I mean by slow? These algorithms are intentionally designed to take time. They require many rounds of computation. For example, with Bcrypt, each cast takes about 100 milliseconds. With Argon2, each cast takes from 500 to 1000 milliseconds. This makes GPU brute force take years instead of seconds. The second option is use memory-hard algorithms like Argon2. Argon2 uses both CPU time and memory. CPUs struggle with memory-intensive operations, making it much harder to parallelize the attack than simple hashing, and increase the cost factor. It controls how many rounds of computation happens. Cost 10 equals 100 milliseconds per guess. That's the default. Cost 12 equals 300 milliseconds per guess. Cost 14 equals 1 second per guess. Higher cost means slower GPU attacks. But be careful. If you set it too high, when a normal user tries to log in, it will take a long time to verify their password. So let me recap what we have covered. We started with the principle of never trusting the client. Always validate server-side, verify user identity and permissions, and recalculate sensitive values like prices, discounts, or totals. We covered SQL injection and three main defenses: parameterized queries, stored procedures, and LO list. Parameterized queries should be your default approach. We discussed rate limiting and how to combine it with account logout, captcha monitoring, and MFA to prevent brute force attacks. We talked about error handling. Log everything internally but return generic messages to users. Never expose stack traces, database details, file path, or internal APIs. And we covered secure storage, focusing on password hashing. Passwords must be hashed, not encrypted. Use salting to prevent rainbow tables and collision attacks. And use slow, memory-hard algorithms like Bcrypt or Argon2 to make brute force attacks impractical. That covers the three parts of web security: frontend, transition, and backend. That's it for today. If you found this helpful, don't forget to like and subscribe. It really helps the channel grow. And if you want to level up your frontend skills, check out my advanced frontend course, link in the description. Thanks for watching, and I will see you in the next video. Bye.